Good morning. Today we're going to talk about algebraic proofs. And we saw in our last unit some examples of geometric proofs. We didn't formalize them, but we did talk about them and we did do a series of them. And we learned that when we do algebra every day, there is a way to justify every step that we take with some formal statements. Hopefully by the end of today, you will know how to construct and write an algebraic and perhaps even a geometric proof. Let's start with some definitions. What is a proof? A proof is a series of logical statements, each statement helping to prove an idea, being justified by given information, definitions, properties, theorems, or postulates. And to refer back to our lesson from last time, an algebraic or geometric proof will use deductive reasoning only. There are two parts to, or there's several parts to a proof. But two fundamental parts are the given information, and that is the if part of a conditional or the hypothesis of a conditional, and it's information that's going to help us prove a general statement. There is also the prove part of our proof. This is the thing we are trying to justify, and we are going to justify this using the given information and our theorems, postulates, definitions, and information. We can even use things that we can determine from a picture. It is always going to be the then part of a conditional or the conclusion of a conditional, and it will never, ever, ever be used as a reason. The thing you are trying to prove can't be used as a reason for proving it. That's a little bit of a circular logic. There are lots of properties that you are going to find very intuitive. You've used them a lot, and I'm going to just show you some examples of some of them. This one is not one of those intuitive ones. This one seems ridiculously silly to a lot of people. It's the reflexive property. And it says that if A exists, then A is equal to A. Example 6 is equal to 6. A is equal to A. Seems silly. You'll see how we use it later. There's also the symmetric property. If A is equal to B, then B is equal to A. It just tells you that the order that you write an equality statement does not matter. So if segment AB is equal to segment BA, then segment BA is equal to segment AB. In an angle example, the order that you write the vertices or the order that you write the points of that angle does not matter because angle CAB is the same as angle BAC. Symmetric property. These should be more familiar. Distributive property, used all the time in algebra. Substitution property, used all the time in algebra. If x equals 3 and y equals 8x, then y is really equal to 8 times 3. Transitive property. This one is somewhat intuitive, but confused with the substitution property frequently. It tells us that if A is equal to B and B is equal to C, then A is equal to C. And it seems pretty straightforward. It's just kind of a strange way that we use this. So if x equals 2 and y equals x, then y equals 2. Addition property just says that I can add the same number or the same quantity or representation to both sides of an equality statement, and the equality of that statement remains. Subtraction property, same idea. I can subtract a constant from both sides or a variable from both sides and retain that equality. I can multiply both sides of an equation by a variable or a constant and maintain equality. And lastly, the division property. I can divide both sides of an equation by the same constant or variable and retain equality. These are the fundamental golden rules of Algebra 1. Do unto one side as you do unto another when solving equations. All right. That's enough mumbo jumbo. Let's actually do a proof, shall we? I'm going to start by looking at the information I was given. I was given that if 7 equals CD and 7 equals EF, remember this is probably the measure of a segment. So I have two segments that both measure 7 units. Then we are asked to prove that these two segments are equal to each other. So I wrote out what my given information is using the hypothesis of that conditional statement. And I wrote down what I was trying to prove, which is the conclusion of my conditional statement. When I'm writing my proof, I always start off with two columns, a statement column and a reason column. The statement column are always going to be statements like your given information or the thing you're trying to prove, and your reasons will come from your theorems, postulates, or from that property, the mathematical properties up above. So I'm going to always start with my givens. Sometimes I use my givens immediately. Sometimes I sprinkle them in when I need them, but it's always okay to start with your givens. I was given that 7 is equal to CD. I was given that 7 is also equal to EF. And the last thing I'm going to do is I'm going to conclude that these two are equal to each other using the transitive property. When you write out your proofs, remember that you are welcome to abbreviate these lengthy words, but you have to use both words or abbreviations for both words, and you have to give me at least enough of an abbreviation that I can differentiate between other possible properties or theorems. Let's try another example. Again, I'm given a conditional statement. If x divided by 4 equals 12, then x equals 48. From that, I'm going to use the hypothesis as my given information and the conclusion as my statement to prove. I'm then going to create my two-column proof, creating a column for statements and a column for reasons. I'll start with my given information. Why can I use the given information? Because it was given. X divided by 4 equals 12. Then I am going to, this is a nice short proof, isn't it? I'm going to go ahead and list my proof statement. X is equal to 48. What justification do I have for saying that X equals 48? Well, I can use the multiplication property, which says that I can multiply two sides of an equation by the same thing, and the result is also an equal statement. So in this case, if I multiply both sides by 4, I end up with X equals 48. The way we undo, or the inverse of division, is through multiplication. Another example with a little bit more of an interesting part to it would be if x times 8 minus 3 equals 4, then 8x minus 3x equals 4. Immediately your brain should think distributive property. Don't be tempted to start doing things you don't need to do. You don't need to simplify inside parentheses. We're not asking to solve this equation. We are just simply doing a proof. So I identify my givens, the hypothesis, and the proof statement is my conclusion. I make my two columns. I identify them as being statements on the left, reasons on the right. I fill in my given information. And then it's a simple two-step proof. I'm going to use distributive property to show my proof statement. They do get more complicated, I promise. And we saw some more complicated proofs when we did the Unit 1 assignments. Let's look at another. In this case, I did not give you a conditional statement that you then have to find the given and prove from. Instead, I just went and gave you a straightforward given. You're given that 8x minus 8 equals 19, and I'm asking you to prove that x equals 9. Create your two columns. Start with your givens, and then ask yourself, what would I logically do next in solving this algebraic equation? Logically, I would add 8 to both sides. So let's do that. I end up with 3x equals 27. Why? Because I used the addition property. Ask yourself, what would I do next? I would divide by 3. By that, I end up with x equals 9, which is what we were trying to prove. And I use the division property to undo that multiplication. These can actually be kind of fun. Let's look at another. Again, I was given a statement, 3 times 2x plus 2 equals 30. I'm asked to prove that x equals 4. I'm going to let you pause the video, work through this, and then come back to check your answers. All right, here's what that proof would look like. I'm going to write my given information. I'll use distributive property, then the subtraction property, and lastly, divide both sides by 6, the division property, and I end up with x equals 4. My next one is a little bit more interesting. There are multiple ways that you could do this algebraically, and therefore there are multiple ways you could prove this. The order that you do some of these steps could be switched around. Do what's most comfortable for you. We are given that A times quantity B plus 2 equals 45 and that A is equal to 3. We're asked to prove that B equals 13. In this case, we have two pieces of given information. We create our proof, 2 columns, and then I like to list, or I did in this case, list both of my givens together. The next thing you could do, you could either do substitution and substitute the 3 with the A, or you could go ahead and use distributive property. Either one will work. I have to do both eventually, and the order does not matter. I chose to do my substitution first. So instead of writing an A here, I replaced part of this statement with the number 3. Then I used distributive property, subtracted from both sides, and divided to conclude my proof. All right, let's keep going. This next one, you are going to have to go back to your property list to really figure out how to do this one. If I am given segment AB, then I want to conclude that AB is equal to AB. I'm sure you're saying to yourself, that is complete nonsensical stuff, but it is a real thing, and we do use it when we are using, especially with triangle proofs. First thing I'm going to do is list my given information. I was given segment AB. Then I'm going to conclude that AB is equal to BA. And I am going to use, I wrote this backwards, I am going to use the reflexive property to do that. Had I left it as AB equals BA, that would have been the symmetric property. Thanks for catching that for me, folks. Let's do another example. This is again an algebraic example where I'm given two givens. Given two pieces of information, and I'm asked to prove that y equals 6. I'm going to start off by creating my 2 columns, and I'm going to label them statements and reasons. I'm going to list out my given information, and then again from here you can choose whether to do that substitution first or whether you would like to do the distributive property first. The order of those 2 steps does not matter. Pause the video, try this, and come back to check your answer. Hopefully you created a proof that looked something like this. Again, steps 3 and 4 could be switched, and it would still be a logical proof and a correct algebraic equation. Simplification. All right, last one. Again, this is very similar to the previous one. I'm asked to prove that y equals 16 using my 2 pieces of given information. There's nothing rocket scientist about this. I just feel like these are a little bit annoying for some students because they don't like to break their simplification of algebraic expressions into such minute detail. And it's also sometimes hard to justify why you're doing it because your brains work really fast and you try to do multiple things at one time. But remember, you have to do one step at a time, and you do need to justify each of your steps. That concludes our study of algebraic equations. We will look into some algebraic proofs. We will look into some geometric proofs in the next unit, and they will be a little bit more interesting. Until then, enjoy